Okay, excuse me, I'm back. We're gonna do part 2 now, or whatever I'm calling part 2. I just wanted to split the video so I could get the first half out more quickly. We'll do the second half now. The second half is just gonna be these two graphs of tangent. Or actually, it looks like it's gonna be one more graph of secant, then we'll do the two tangents. All the while, we'll always be talking about domain and range, so you'll have that background too. We'll be talking about writing the equations as well. Alternate equations if necessary, but it's not really necessary here. Okay, so here's another secant. How are we going to go after this one? I think we're going to do the exact same thing. We're going to label this local min. Where is that? Make sure you note the scale we're going by. It takes 1, 2, 3, 4 boxes to get to 1. So everything is a quarter. This is 1, 2, 3, 4 quarters. 5, 6, 7, 8, 9 quarters. That's that value, negative 9 quarters. All right, now we've got the local maxes right here. So if this is 9, 10, 11, 12, 13, 14, 15 quarters, negative 15 quarters. So perhaps more importantly, the total distance between these things is 6 over 4, which halves, or well, 6 over 4 is the same as 3 over 2, which chopped in half would be 3 over 4. So that seems to be giving me an A value of 3 over 4. And that also tells me that our midline must be right smack dab in the middle. So we are going to want to just go 3 over 4 units down. So from 9, that would put me at 12. 15, if I went up, would put me at 12. So here's 9, 10, 11, 12. So our midline is actually right here at negative 3. So that's a D value of exactly negative 3. Let's find our B value. And let's remember that our B value comes from our period. And our period we got to find for ourselves in the grid. So again, I think I'm going to use my same old trick. I'm going to take this value. It only needs to be pulled 2 units left to put it right on the axis. This value sort of coincides with it. So if I were to pull this guy left and the other guy left so that they stay together, essentially what's happening is it's like I'm sewing these values together. And as I pull this over to the axis, I'm doing that just for ease of finding how far it is. Because if I put this one at 0, this is 0, then this one ends up at 2 pi over 3. Then guess what the distance from 0 to 2 pi over 3 is? It's 2 pi over 3. So that's our period. And that's kind of the cheap life hack way to get your period. So our period's 2 pi over 3. And I think it is obvious, hopefully, that means our B value is going to be 3. But we can do the math. Our B value is going to be 2 pi divided by the period. That means 2 pi times 3 over 2 pi. The 2 pi's instantly cancel out. So we've got a B value of 3. And again, we said the C values will vary. Based on which function we choose to model. So for a first equation, it doesn't matter. Let's write a secant equation. Who cares? Pretty confident it should have 3/4 as a coefficient. Pretty confident it should have 3 here. There should be an x. There should be a phase shift. There should be a vertical shift 3 units down. So all that's well and good. Our phase shift for secant, we said secant relates to cosine. Our phase shift should map us onto one of these here, local mins. Why should it do that? Because again, for what I hope is the last time ever, our graph is entirely based off of a sinusoid. And secant being the reciprocal of cosine means it should start in the same place that cosine starts, and cosine starts at a max. So if you can continue visualizing these sinusoids, you're going to be able to find those starting points. So where are we? We're right here. Where's here? Well, this is pi over 3, and there's 4 of them. So I guess if we multiplied pi over 3 by a quarter, that's going to tell us that our scale is currently pi over 12. So this one is 2 pi over 12 or pi over 6. So that phase shift ought to work for us. We're going to push pi over 6 to the right, so it'll be minus that value of pi over 6. So there's one function. We said we can write another function by just switching over to cosecant. All right, so cosecant starts where? Well, cosecant starts where positive sign would start. Positive sign starts on the midline value, but going up from there. So when I say midline value, I mean the places where we have asymptotes. So right here, you can see that as the start of a sine wave, probably. So this is supposed to hit here, come down, hit here, go back up and hit here. So our cosecant function is going to want to start on an asymptote. So I'm going to start it right here. And again, in a kind of boring way. Now this just happens a lot because our graphs are symmetrical. But our first phase shift was just pi over 6 to the right. Our next phase shift is going to be pi over 6 left. So it's negative pi over 6, which means we're going to use a plus here. But that's it. We did it. We did that one. I did say I would do domain and range, so I'll do it again. Where's it grabbing that? Undo. Shrink. All right, now we can do domain and range. All right, range first. Range is always going to be negative infinity up to these little extrema. This one here occurring at negative 15/4. So hard bracket. Then do the union of that with hard bracket. The bottom of this curve, which is at negative 9/4. And then of course that curve is running up to infinity. So we continue. So that's our range. Our domain is another one of these all real numbers except things. And we're still just excluding the asymptotes. So there's an asymptote right here. If we're counting by over 12s, by pi over 12s, then it's 1, 2, 3, 4, 5, 6. So 6 pi over 12. So this is pi over 2. This asymptote right here. It's at pi over 2. So we'll list that as the first asymptote, pi over 2. Then for secant or cosecant equations, we want to add on just half of a period to get to the next asymptote. So we had a period of 2 pi over 3. That means half of our period is 1 pi over 3. So we need to add on pi over 3k, where k is an element of the set of integers. So there's your domain and range. And here are your equations. So pretty good. So now we get to switch gears and we get to do these tangent ones. These ones are especially important because I felt like the homework problems that involved tangent were pretty sloppily rendered. They were just kind of grabbed from Desmos, and some of our critical values fell sort of between grid lines. And, you know, if you remember, they weren't even at the halfway mark. They were at like the 1/3 mark, right? So that was pretty rough. But all of these, if you look, I tried really, really hard, you know, to make sure that all the critical values, were very visible. There's a big honking dot where all the critical values are. And they all fell right on grid lines. Like this is clearly right at 2 pi with a y value of 5. Like, you know, if you guys can't do this, it's not because the graph is unclear. It's because you didn't study hard enough. So now that we've got a good one to really practice with, let's practice. By the way, that means click the pause button again and do it yourself. Stop listening to me and try it yourself. Okay, don't say I didn't warn you. Now I got that song in my head. Oh, Taylor Swift. Yeah, my wife's been listening to a bunch of that. So, yeah. So the A value, how do you find that? It's just the distance between the midline and these other values, these values that fall sort of a quarter of the way through our period and 3/4 of the way. I still do not have a good name for these guys, but we can't call them maxes and mins anymore because they surely are not that. But this distance up and down from the midline, that remains our A value. And we can read off the grid that if our x scale is 1, then we're just counting boxes. And there's 2 boxes, so A is 2. All right, next we would find B. B still comes to us courtesy of the period. And the period is going to be asymptote to asymptote. Let's try that cheat again, where basically you just circle these guys. You know what? Let's not cheat. Let's try to do this the right way. So the right way would be to actually find these x coordinates and then subtract them. So if this pi here is 1, 2, 3, 4 units, then every unit must be pi over 4, right? And so that means this guy is 3 pi over 4. It means this guy over here, well, who's this guy? He's 20 pi over 4. So what's this? It's 21, 22, 23 pi over 4. So if for some reason you really want to know the actual x coordinates of these vertices, and if you really want to know that the period, I'm writing behind my face, aren't I? Yes. See, I don't see my face. Just you guys see my face. But there you go. Another way to find the period, of course, is just to subtract those x values. I think it behooves us to consider absolute value. But if you always just do the big one minus the small one in that order, then of course it'll always come out positive. But period should always be positive, so just putting absolute value bars on it ensures that that happens. But we're just going to do the 23 pi over 4 minus the 3 pi over 4. Lo and behold, we get the absolute value of 20 pi over 4, which is 5 pi over 4. Super psych, it's 5 pi. It's straight up 5 pi. All right, so now for my little life hack again. Often what's going to happen is, if you just take this point and drag it onto the y-axis, 1, 2, 3 boxes, then obviously the other one has to go 3 boxes too. 1, 2, 3 boxes. And many, many times, very often, that point is going to land on one of the actual labeled grid markings. And so the distance then from here to here is 5 pi, and your period's 5 pi. You don't have to do any math. You can actually just read it right off the grid more easily. And so that's that. What else could we have done? I don't know. That's a good method. You should do that. All right. So guess what? Then if our period is 5 pi, then our b value is going to be pi divided by the period, which is going to be pi divided by 5 pi, which is giving us a b value not of 5. I have a feeling that after a year of virtual instruction, I'm going to have a ton of kids who think that if they cancel out the entire numerator, the answer just is the denominator. But no, when you cancel out the pi's, you're still left with a factor of 1 in the numerator. This is going to be 1/5, not 5. Okay, we did it. Great. Super proud of us. Guess what the c value is? Will vary. And it's going to vary depend on whether we are writing an equation using tangent or writing an equation using cotangent. So I'm not going to address that. But we do need a d value. D value tends to be simple. The d value is the distance from the x-axis up to that midline. It's how far we had to translate. And this one happens to be nice and plainly labeled for us. It's 3. Positive 3. So that means we can write our first equation as 2 times the tangent of 1/5 x plus or minus something plus 3. So I left out a couple of things. And the first thing is you can't just decide whether you want to use positive tangent or negative tangent, because positive tangent is going to want to go like this. And it's going to want to increase. And our function decreases. So we literally cannot model this graph using a positive tangent function. It has to be negative to make it decay. So all right, we got the negative. Now we just need our phase shift. And our phase shift for tangent is a midline point. And again, you've got sort of carte blanche to pick any midline point you want to pick. There's this guy right here, or there's that guy there. I really don't care which one you pick, but again, my guidance is maybe pick the one that minimizes the actual shift. So we could shift left however far this is, or we could shift right however far this is. And again, the shifting right is the longer one, so let's go left. And how do I actually find this? Well, again, just figure out what your scale is. If this is pi and it's chopped into 4, then we're counting by pi over 4s, which means we are phase shifting 1, 2, 3, 4, 5, 6, 7. 7 pi over 4 is that point there. So 7 pi over 4 will phase shift us to where we want to be. And we want to go left, which means we need this to be a plus. Again, because going left means it's negative. And our sign has a built-in negative. So we end up with x minus negative 7 pi over 4, which turns into plus. I hesitated on 4 because it's doing that thing again where it looks like a 9. Don't anybody look at this and think it's a 9, because it ain't. It's a 4. Hopefully that made sense. We got to do domain and range. And the good news is, this has actually gotten a little easier rather than harder, because our range no longer has any restrictions at all. It's just straight up all reals, so that helps. Our domain is going to follow the exact same order that the other one did. We're going to say it's all real numbers, but then we're going to say, well, actually, it's not all real numbers. It's all real numbers except for the x-coordinates of our asymptote. So we'll find an asymptote. This one right here seems nice, and I see that it's living at 3 pi over 4. So I will fill that in. And then to eradicate all the other asymptotes, I just add on a full period. A period would map me from asymptote all the way to the next asymptote. And we already did the math on our period. Our period is 5 pi. So we'll add in 5 pi times k, and we shall stipulate that k must be an integer. Certainly can't be a decimal or a fraction. Oh, I got ahead of myself. We still need our secant equation. So my bad. Let's get that second equation. We'll grab all this good stuff. Yeah, that's what I was afraid of. Okay, you. Get separated. All right, so now we'll grab all this good stuff. We'll shrink it down. Put it over there. I don't know why I shrank it. We'll make it as big as we can again. So there's your domain and range. And then, my apologies everyone, let's write our cotangent function, which will of course be positive, because cotangent naturally decreases. Cotangent is a decreasing function, even when its coefficient is negative. So we're going to go positive 2 times the cotangent of 1/5 times x plus or minus something plus 3. All right, where does cotangent now want to start? It wants to start on an asymptote. There's an asymptote right here. We've already figured out that is 3/4. So that's going to be our phase shift. It's going to be x minus 3/4. And that ought to do it. So there's my one equation in tangent, which needed a negative coefficient so that it would reflect and decrease. I've got my one equation in cotangent, which does not need a negative because it naturally decreases. I've got the right b value, I hope, the right d value, and I've got the right phase shift for the right function. We have one more. Okay, same thing. I'm giving you another tangent. The 3 dots are playing, if you guys can complain about this, then I guess you're just complainers. But the dot fell on top of the pi, so maybe it's a little bit obscured But holy cow. This is as good as it gets, children. I even put little arrows on for you. You guys think those arrows came out of the computer? Nope. I made each of these little arrows individually, and I meticulously placed them right where they go, like I was working on a delicate Fabergé egg. Right, guys? Right, period 8? You know what I'm talking about. Anyway, let's do it. I mean, you do it. Push the pause button. Do this problem yourself if you haven't already. All right. So, you guys know the drill. Let's find A. Let's find B. Let's not find C, but let's do find D. We're not going to find C because C will vary. All right, A is a piece of cake. A is the vertical change between the midline and these other points. Okay, that appears to be 1, 2, 3. So I'll write down 3. Oops, I got it wrong. What a shame. I didn't read the Y scale, which is obviously a half. So be careful. Don't just count boxes, everybody. You got to actually pay attention to the scale. If every box is worth a half, then my A value is 3 halves, not 3. Be careful. The B value comes from the period. I'm going to skip that for the moment. Let's just find our D value. We said our D value is just the vertical shift from the x-axis down to the midline. So that's 1, 2, 3, 4 boxes. So it's 4 units down, right? Up, gotcha again. The scale's a half, remember? So 4 boxes is actually a change of 2. Don't count the boxes. Read the axis if you can. It says right here that the distance we traveled is 2 units down, right? So maybe don't count the boxes. Maybe you actually look at the axis. All right, but those are easy. Those are nailed down. So now let's get our period. It's called the period. So hey, look, here's a handy dandy critical point sitting right on the y-axis for us. So what, pray tell, is the distance to the next corresponding point? Oh, did you say pi over 3? That's your period then. If you can find those points, if you can find a critical point sitting right on the y-axis, you should use it, right? Now, did we have that luxury last time? We did not. The point on the y-axis was not a critical value. But so what do? We found 2 critical values. In this case, we used the asymptotes. And we literally just looked at it and went, if I drag this 3 units left, it'll be on the asymptote. It'll be on the axis. So I'll just drag this one 3 units left. And in doing that, we found ourselves sitting right at 5 pi. And then we knew the period was 5 pi. I did talk about the other way to maybe more rigorously do it by actually finding the x's and subtracting and all that, but you just almost never need to do that. So just look at the picture. All right, finally, the period's pi over 3. That means that B is 3, right? I always doubt myself. Let's use the formula. B, we decided, is pi divided by the period. So of course that's pi divided by pi over 3, meaning multiplied by 3 over pi, meaning the pi's cancel, meaning we get 3, like I said. So we now have everything we need except for the phase shift. So let's flesh out our equations. We're going to write one tangent equation. That tangent equation is going to need to be negative again because I did give you another decreasing function. I probably should have given you one that decreased and then had the other one increase, but doesn't matter. It doesn't. You guys should know. You guys should know what to do. So this one decreases again, which means that the tangent function should be negative. So we'll go negative 3 halves as our coefficient. So it's negative 3 halves. Then we need that b value of 3. The phase shift that we need for tangent is whatever phase shift maps us onto a midline value. So I'm spotting this one. This one's too far away. I see this one. And it's happily sitting at negative pi over 12, so it'll be plus pi over 12. And then of course I need to drag everything down 2 units, so minus 2. There's my tangent function. My cotangent function will be positive it'll still feature a b value of 3, I want to map onto an asymptote. Oh rats, it's that thing again where it's the same. That wasn't how this one worked, was it? Okay, good. So here I didn't have that symmetry over the y-axis where the two phase shifts were just the same number plus or minus. That happens a lot, but it doesn't happen here. We had 7 pi over 4 and we had 3 pi over 4, so that should scratch our itch for not having this dumb situation where one phase shift is pi over 12 left and the other one's pi over 12 right. That always feels kind of bad, but it's the way it is. So pi over 12 minus 2. We're done. We wrote our equations. So nothing left to do now but domain and range, and I hope that you get it by now. So domain and range. The range is all real numbers. Literally the easiest question I could ever ask. Now the domain is literally all real numbers, except pick an asymptote, pi over 12 standing out. Now add to that the distance that will map us onto every other asymptote, and that distance is a full period, and our period is pi over 3. Pi over 3 is what we said. Yeah, so plus pi over 3 times k, where k is an element of the set of integers. Put that in a little cloud. Put these in a little cloud. Okay, and finally we're done. I'm not doing your homework. I know. There will come a day when I do your homework again. I know it's probably helpful, but I also know that you guys are probably exploiting the crap out of it. And I just do not believe that you guys are putting in as much thought as you should. And I think tomorrow, we'll see the burden of proof as suddenly only half of our homework is actually done, and you guys are begging for an extension. We got to get back to, doing our homework, getting to class on time. We got to get back to asking intelligent questions. So sorry, we're trying this. I'm not going to do your homework for you, at least for a minute, and we'll get you guys back to doing it yourself. Anyway, I'm sorry that it's late. I hope you're up studying anyway. Get to bed soon, hopefully by like 10. Get to bed by 10, that's fine, in my opinion. If you have questions, I'll try to keep, what? I guess I'll try to keep my email open. You can throw an email in, and hopefully I'll hear the notification, and I'll try to get right to you. But we're taking the quiz tomorrow, so do your best to be prepared. See ya.